For about a century, the atom was this abstract thing. We understood it with math, with theories, but it was always this ghostly realm of probabilities that seemed like we could never, ever truly see. But what if you could? What if you could take a direct picture of an atom's inner workings? Well, today we're going to dive into the incredible breakthrough that did just that. Just look at this. This is a real image of the inside of one single hydrogen atom, captured back in 2013. I know, it kind of looks like ripples in a pond, right? But what you're seeing is a genuine glimpse into the quantum world. Now, the big question is, how on earth do you photograph something that, according to everything we know from quantum mechanics, shouldn't be able to sit still for a picture in the first place?
For the longest time, our entire understanding of the atom was built on these beautiful but totally abstract equations. We knew the rules of the game, so to speak, but we could never actually watch the game being played. This experiment, it changed everything. It took the mathematical blueprint of an electron and turned it into a direct, visible image for the very first time.
And that really gets to the heart of the problem. See, an electron isn't some tiny little planet zipping around a sun. It's more like a cloud of probability. It exists in this whole region where it might be. Trying to pin it down to one spot is like trying to take a picture of a ghost. It's kind of everywhere and nowhere all at once. So, how would they pull it off?
Okay, so to understand the photograph, we first have to wrap our heads around what exactly we're trying to see. And that means we need to talk about the electron's fundamental instruction manuals, something called the wave function.
So the wave function isn't the electron itself, and that's the crucial thing to get. Instead, it's the recipe, the mathematical formula that tells you all the possible places the electron could be. Where the wave function is strong, you've got a good chance of finding the electron. Where it's weak or zero, not so much.
Here's an even better way to think about it. The wave function is like a treasure map. It doesn't actually show you the treasure chest, but it highlights all the spots on the island where the treasure is most likely to be buried. That map is what these scientists set out to photograph.
Now, what's really wild is that this experiment, which seems so futuristic, didn't come out of the blue. The idea that you could actually take a picture like this was predicted decades before anyone managed to do it. This whole thing is really a story about a long-shot theory finally being proven spectacularly right.
It all started way back in 1981. A team of physicists basically said, hey, if you set up an experiment in a very specific way, you could essentially project an electron's wave function onto a screen. You could magnify its quantum structure so we could actually see it. People tried it, of course. Through the 90s and 2000s, they tried with bigger atoms like xenon and lithium, but things are just too messy. There were too many electrons getting in the way. It wasn't until 2013 that a team finally cracked the code by going back to the absolute basics. So why hydrogen? Why did it work when all the others failed? Well, because hydrogen is basically the universe's cheat code for quantum physics. It only has one electron, so right away you get rid of all the complicated interactions that muddy the waters. But here's the real magic. When you stick a hydrogen atom in an electric field, the math that describes its electron becomes exactly separable. All that really means is that the tiny, intricate pattern the electron has near the nucleus gets perfectly preserved and blown up, magnified as it flies away to a detector. It's a perfect projection.
Okay, so they had their atom. Now, how did they actually build this thing? To take this picture, the scientists had to create this incredible device. You can think of it as a quantum microscope, designed to capture that ghostly probability map of the electron. And this is it. I know, it looks a little complicated, but the core idea is surprisingly elegant. You've got a source of hydrogen atoms over here, a bunch of electric fields to steer things, a couple of lasers to give the atom a kick, and then a 2D detector at the very end to act as your photographic film.
So let's walk through it. First, they shoot a beam of hydrogen atoms right into a strong electric field. Then, zap, a laser hits an atom, boosting its electron into a very specific high-energy state. Then a second laser comes in and gives it one last gentle nudge, just enough to pop it free from the atom. That big electric field then grabs the escaping electron and acts like a giant lens, guiding it straight onto the detector. And here's the magic trick. The spot where it lands isn't random. You do this millions of times, and the electrons build up a pattern on that detector, and that pattern is a direct, magnified image of the wave function they just left behind.
All right, now that we know the how, let's go back to those incredible images and finally decode what they're actually telling us. This is that amazing moment when the theory finally became a visible reality. And here is the payoff. Seriously, just look at this. In each of these rows, the image on the left is the theoretical prediction.
what the math from decades ago said it should look like. And on the right, that's the actual data from the detector. They are a near-perfect match. The theory didn't just get the gist of it. It predicted the exact pattern, right down to the number of those dark rings.
In fact, the code is incredibly simple to read. These dark rings are called nodes. They're just places where the probability of finding the electron drops to 0. And the number of rings you see tells you the exact quantum number of the electron's energy state, something called N1. If you see 1 ring, N1 equals 1. 2 rings, N1 equals 2. The photograph isn't just a pretty picture. It's a direct readout of the atom's quantum state.
But the story doesn't stop there. As it so often happens in science, when the researchers looked a little closer at their data, they found something else. Something extra. Something that, from a classical physics point of view, should be completely impossible.
So take a look at this comparison. The picture on the left is what they saw when the laser was tuned just a little bit away from the electron's perfect energy level. But the image on the right, that's what happened when they tuned the laser to the exact resonant frequency. Do you see it? See how much farther out those rings on the right go? The electron is showing up in places it just, classically, shouldn't be able to reach.
The physicists who first predicted this called it a remarkable tunneling effect. Think of it like this. The electron is stuck in a valley, and there's a huge mountain range, an energy barrier, all around it. Classically, if it doesn't have enough energy to climb over the mountain, it's stuck forever. But in the quantum world, if you hit it with that exact resonant frequency, the electron can just tunnel straight through the mountain, appearing on the other side and traveling way farther out to the detector. And this wasn't some tiny, subtle thing. The signal they got at the detector, the number of electrons actually making it there, was a staggering 10 times stronger when the laser was perfectly on resonance. This is what proves the image isn't just some faint, ghostly interference pattern. No, it's a direct, powerful, macroscopic projection of that tiny quantum state, supercharged by this tunneling effect.
So what's the big takeaway here? Why does this all matter? Well, for one, this was the very first time anyone had ever directly seen the structure of an atom's wave function. It was just this beautiful, stunning validation of quantum theory, including its weirdest predictions like tunneling. And it's more than just being right. It opens up a whole new door. It gives us a brand new tool to actually visualize the quantum world. For the first time, we literally have a camera that can take a picture of the ghostly blueprint of reality itself. And that forces us to ask a really exciting question. Now that we finally know how to look, what other secrets is the quantum world waiting to show us?